Hey, today I'm talking about a new circuit element called a capacitor. So far, I've only discussed voltage and current sources which generate energy, and resistors which consume it, converting it to heat. Capacitors, on the other hand, are energy storage elements. This means that any energy accepted by a capacitor can be extracted later on for use in the circuit. It's important to note that they don't actually generate any new energy. The only energy you can get out is energy you've already put in. Therefore, like resistors, we call them passive circuit elements. The circuit symbol for a capacitor looks like this. These two are the most common ways you'll see this drawn, with the left being overwhelmingly the most common. This other way, with the curved bottom plate, is usually describing a certain type of capacitor, but a lot of the times just the general symbol will be used no matter what the physical construction of the capacitor is. You sometimes might also see a plus symbol drawn on one of the plates to indicate polarity. But the main takeaway here is that the capacitor circuit symbol is essentially just two parallel lines with a gap in between. Electromagnetic field theory is the study of electrical charge. In circuit analysis, we simplify many of those concepts by absorbing them into circuit elements. And capacitance is a circuit designer's way of describing energy stored in an electric field. Now, if talking about fields scares you, that's okay. While I might wind up talking about fields in a later video, it's better if we just accept it for now and narrow our focus to circuit elements themselves. Okay, so before I go any further, I want to quickly lay down some verbiage. As I just mentioned, the fundamental physical phenomenon at play is the storage of energy in an electric field, aka capacitance. The circuit element we use to describe this behavior is called a capacitor, and circuits, systems, and other situations in nature that exhibit this behavior are said to be capacitive. Again, one more time, capacitance, capacitor, capacitive. Capacitors are created by separating two conductors with an insulator. The insulator could be one of any number of materials like air, polyester, polypropylene, mica, etc., and is called a dielectric. The most common structure we use is called a parallel plate capacitor, and it looks something like this. Imagine the two parallel rectangles to be the conductors and the space in between to be the insulating dielectric. And these lines and dots I've drawn off to the side are just our ideal wires from our circuit elements. I'm trying to focus less on the physics and more on the circuits in this video, so I'm going to omit the derivation, but I'll show you a formula that describes its behavior. The capacitance of the ideal parallel plate capacitor is described by this formula. C equals epsilon times A divided by D. Now, first and foremost, I have to give a disclaimer about this drawing compared to this formula. This formula describes the behavior of an extremely idealized parallel plate capacitor. The main deficiency in my drawing is that for this formula to be true, it's required that the length of the plates is much, much greater than the distance between them. So while I've done a bad job drawing this, you need to imagine that the length of these conductors extends off essentially to infinity. And therefore you can imagine how in practice, the spacing d could be incredibly small. With all those assumptions out of the way, we can finally analyze this formula, which essentially tells us three things about the capacitance. The first is the proportionality to the area of the overlap shared by the conductors. This means the more conductive material there is forming a gap with the other conductor, the more capacitance. And in this case, the variable A describes the area of overlap. And as far as how that relates to this drawing, A is the product of the length and the width of the plates. The length L is pictured here as I've drawn it, and you have to imagine the width extending up out of the page and down into the page. The second is the inverse proportionality to the distance between the conductors. This means that the capacitance increases as the conductors get closer together. And third is the dependence on the dielectric material as denoted by the constant epsilon. The dielectric constant is composed of two parts. The first is denoted epsilon naught and is also known as the permittivity of free space. You can think of this as the dielectric constant of a vacuum. This value is then modified by a so-called relative dielectric constant to describe the energy storage capability of other materials. And here I've put together a table of some cool examples of relative dielectric constants. Most of the time we can approximate air as having the same dielectric constant as a vacuum, which is why the relative constant is just 1. Capacitors are formed by objects of all shapes and sizes. In fact, as one of my graduate professors once told me, any two objects in the universe form a capacitor. And while technically correct, this is definitely disingenuous when it comes to circuit design. Yes, there are times when we need to worry about how our circuit interacts with the outside world, but we're never going to be concerned about our conductor forming a capacitor with the metal on Pluto and the vacuum of space between them. And one more distinction I should probably make is that although it's true that any two given objects do have capacitance between them, albeit arbitrarily small, not all capacitors are parallel plate capacitors. Parallel plate capacitors are some of our favorite to work with in electrical engineering for a few reasons. One being that they're extremely easy to analyze and talk about, and another is that in the physical implementation of our circuits, parallel plates are very good at cramming a lot of capacitance into the smallest possible space. Hey guys, one thing I totally forgot to do earlier is to give the actual value for epsilon naught, or the permittivity of free space. In case anyone's interested, it turns out that epsilon naught is approximately equal to 8.85 times 10 to the minus 12. And the units here are farads per meter, farads being the unit of capacitance. It's also worth noting that epsilon naught is a cosmological physical constant. I hope this was a helpful introduction to the idea of capacitance and capacitors, and I think that in the next video I'll finally start talking about the voltage and current relationships, so that we better understand how we can include capacitors in our circuit designs. With that being said, thank you guys for watching and have a great day.